Hello, and welcome to Silent Science. If you've landed here, chances are you're winding down, resting your eyes, or simply searching for something peaceful to end your day. Whether you're curled up in bed, taking a deep breath after a long evening, or just letting your mind wander in the quiet time, glad you're here. Tonight, we're drifting far from Earth, into the calm, ancient dark of the cosmos. A place where stars are born, not with a bang but with silence, gravity, and time. We'll explore how cold clouds of dust slowly gather, how invisible forces shape light, and how somewhere in the new sun begins to glow. Don't worry, there's no rush, no tests, just the soft unfolding of the universe, one whisper at a time. So get comfortable, breathe in, and let's gently float through the mystery of star birth. This is science, softly spoken. The cosmic cradle in the vast emptiness of space, where silence reigns and time stretches beyond comprehension. A quiet miracle begins. It starts not with a brilliant explosion or a blinding flash, but with something far more subtle, a drifting cloud of gas and dust, floating in the darkness like an unseen giant. These interstellar clouds, known as molecular clouds, are the birthplaces of stars. They stretch across light years, their immense size dwarfing even our own solar system. Yet, to the naked eye, they appear as nothing more than faint smudges against the starlit sky. Within them, however, an intricate dance of gravity, pressure, and chemistry is already unfolding. These clouds are composed mostly of hydrogen, the simplest and most abundant element in the universe. But they also contain traces of heavier elements: carbon, oxygen, nitrogen, left behind by generations of dead stars. These remnants drift through the void, waiting for the right conditions to begin their transformation. For now, the cloud remains cold and still, its particles moving sluggishly in the frigid depths of space. Temperatures within these regions can drop below -260 degrees Celsius, just a few degrees above absolute zero. At this temperature, atoms barely move, and chemical reactions occur at a near standstill. But despite the apparent lifelessness of this cosmic cradle, it holds the potential for creation. The first step in the birth of a star begins with motion. Though the cloud appears tranquil, tiny disturbances ripple through its shockwaves from distant supernova, gravitational tugs from passing stars, or the gentle push of galactic winds. These disturbances create small density variations, causing some regions of the cloud to become slightly more massive than others. Gravity, ever patient, takes notice. In these denser pockets, the pull of gravity grows stronger, drawing in more gas and dust. As matter accumulates, the core of the cloud begins to contract, slowly collapsing under its own weight. This collapse is not immediate. It can take thousands, even millions of years for a cloud to begin forming a star. But once it starts, the process accelerates. As gas falls inward, it heats up due to increasing pressure. The core becomes denser, and the surrounding material forms a swirling disk around it. This structure, known as a protostellar disk, will one day give birth not only to a star, but possibly planets as well. Meanwhile, magnetic fields and turbulence within the cloud resist the collapse, creating a delicate balance between inward pull and outward resistance. Some parts of the cloud fragment into smaller clumps, each destined to become a new star. Others remain part of the larger structure, feeding the growing stellar embryo at its center. As the core continues to contract, it emits faint infrared radiation, an invisible glow that betrays its presence to those who know how to look. Astronomers use powerful telescopes to peer into these dark clouds, detecting the hidden warmth of newborn stars long before they ignite. These observations reveal a hidden world of activity, where the seeds of future suns are taking shape beneath layers of dust, and so, in the silent expanse of space, the first chapter of a star's life begins not with fanfare, but with a slow, steady gathering of matter. The journey from cold, dark cloud to blazing star has started, and though the final act is still far away, the stage is set for one of the most profound transformations in the universe. The pull of gravity, the silent architect of the cosmos, now takes center stage. As the densest regions of the molecular cloud continue to draw in surrounding gas and dust, the process of collapse intensifies. What was once a relatively uniform distribution of matter begins to shift, reshaping the cloud into a complex web of filaments and knots. These structures form as gravity pulls material toward regions of higher density, while the opposing forces of pressure and magnetism attempt to resist the inevitable. It is a cosmic tug-of-war, where the relentless force of gravity slowly overcomes the resistance of the cloud's internal forces. Within this evolving landscape, the initial collapse of gas marks the beginning of a critical phase in star formation. As gravity draws more mass inward, the central region of the cloud becomes increasingly compressed. The outer layers, still loosely bound, begin to fall toward the center, accelerating under the growing influence of gravity. With each layer that collapses inward, the density of the core increases, and the temperature begins to rise. The once cold cloud, which had remained nearly motionless for eons, now stirs with movement as streams of gas spiral inward, drawn toward the nascent protostar. This inward flow is not entirely smooth. Turbulence within the cloud creates swirling eddies and vortices, much like whirlpools in a river. These turbulent motions add complexity to the collapse, redistributing angular momentum and shaping the way material flows toward the center. Some regions experience rapid infall, while others lag behind, forming pockets of slower-moving gas. The interaction between gravity and these dynamic forces ensures that no two collapsing clouds behave exactly the same way. Each stellar nursery is unique, sculpted by the specific conditions present at the moment of collapse. As the collapse progresses, the core of the cloud undergoes dramatic changes. The increasing density causes collisions between gas particles to become more frequent, transferring energy and raising the temperature. While still far from the searing heat of a fully formed star, the core now glows faintly in the infrared spectrum, betraying its growing warmth to sensitive astronomical instruments. This phase marks the emergence of what scientists call a protostera dense, hot ball of gas at the heart of the collapsing cloud. Though not yet a true star, the protostar represents the first tangible step toward stellar ignition. Surrounding the protostar, a flattened disk of gas and dust begins to take shape. Known as the protostellar disk, this structure plays a crucial role in the ongoing evolution of the young star. As material continues to fall inward, some of it does not reach the protostar directly, but instead settles into orbit around it, forming a rotating disk. This disk will later serve as the birthplace of planets, moons, and other celestial bodies, making it a vital component in the formation of entire planetary systems. Despite the progress made thus far, the journey toward becoming a full-fledged star is far from complete. The protostar continues to gather mass, drawing in more gas from the surrounding cloud. However, this process is not without challenges. As the core contracts further, the pressure within it rises, counteracting the inward pull of gravity. This pressure comes primarily from the thermal energy generated by the compression of gas. The hotter the core becomes, the more resistant it is to further collapse. If the pressure builds too quickly, it could halt the contraction altogether, preventing the formation of a stable star. To overcome this resistance, the protostar must find a way to release excess heat. Radiation carries some of this energy away, allowing the core to continue contracting. Additionally, magnetic fields embedded within the cloud play a role in regulating the flow of material. These fields help channel gas along structured paths, guiding it toward the protostar, while also helping dissipate angular momentum. Without this careful balance, the collapse might stall, leaving behind only a failed star, an object too small and cool to sustain nuclear fusion. As the protostar continues to grow, astronomers observe distinct phases in its development. Initially, it exists in a deeply embedded state, shrouded by thick layers of dust that obscure its view from optical telescopes. Only by observing in the infrared and radio wavelengths can scientists peer through the veil of gas and dust to witness the early stages of stellar birth. Over time, as the surrounding material disperses and the protostar matures, it begins to emerge from its cocoon, revealing itself as a luminous young star. Yet, even as the protostar approaches the threshold of true stardom, the environment around it remains dynamic. Jets of high-speed gas erupt from its poles, carving channels through the surrounding cloud. These outflows, driven by magnetic forces and the rotation of the protostar, serve both to clear away excess material and regulate the rate at which gas continues to fall inward. These energetic bursts mark another milestone in the star's formation, signaling that the core is becoming increasingly active and energetic. With each passing moment, the protostar inches closer to its defining moment, the ignition of nuclear fusion. But before that pivotal event occurs, the young star must navigate the next phase of its evolution, where the balance between gravity and pressure determines whether it will shine as a true star or fade into obscurity. The heat builds. A star awakens as the protostar continues its slow but inevitable transformation. The temperature at its core climbs steadily higher. The immense pressure exerted by the surrounding layers of gas compresses the innermost regions, forcing atoms closer together with each passing moment. At first, this increase in temperature is gradual, imperceptible on human timescales. But, in the vast cosmic timeline, the pace quickens. The protostar, once a cold, dense clump of gas nestled within the molecular cloud, now radiates increasing amounts of energy. Its glow, previously confined to the infrared spectrum, begins to shift toward visible light, hinting at the immense changes occurring within. The rising temperature triggers a cascade of physical processes deep inside the protostar. As the core becomes denser, the random motion of gas particles accelerates, leading to more frequent and violent collisions. These collisions transfer kinetic energy, further heating the interior. Despite the intense compression, the protostar remains opaque, cloaked in layers of gas and dust that prevent direct observation. However, astronomers have developed sophisticated techniques to peer into these hidden realms. By analyzing the spectral signatures of emitted radiation, they can infer the conditions occurring deep within the collapsing cloud. One of the most significant developments during this phase is the onset of deuterium burning. Deuterium, a heavy isotope of hydrogen, fuses at lower temperatures than regular hydrogen, making it the first fuel source to ignite in the protostar's core. When the temperature reaches approximately 1 million degrees Celsius, deuterium nuclei begin to collide and fuse, releasing bursts of energy. This reaction serves as an early indicator that the protostar is approaching the threshold of true stellar status. Unlike the sustained fusion that powers mature stars, deuterium burning is short-lived, lasting only a few million years before the supply is depleted. Nevertheless, it marks a crucial turning point, as it provides the first glimpse of nuclear activity within the forming star. Meanwhile, the protostellar disk continues to evolve. Material spirals inward, feeding the growing protostar while simultaneously giving rise to complex structures within the disk itself. Dust grains coalesce into larger particles, setting the stage for planet formation. The disk becomes a dynamic environment, shaped by magnetic fields, turbulence, and gravitational instabilities. These forces work together to redistribute angular momentum, ensuring that gas continues to flow inward rather than remaining locked in orbit. Without this redistribution, the protostar would struggle to accumulate enough mass to ignite as a true star. As the core temperature climbs past 10 million degrees Celsius, the conditions necessary for hydrogen fusion finally begin to take hold. Hydrogen nuclei, stripped of their electrons in the extreme heat, move at incredible speeds, colliding with increasing frequency. When two protons come close enough to overcome their mutual electrostatic repulsion, the strong nuclear force binds them together, initiating the fusion process. This reaction releases an enormous amount of energy, marking the moment when the protostar officially transitions into a true star. The ignition of hydrogen. Fusion is not an instantaneous event. Instead, it unfolds gradually as the core stabilizes and begins to generate energy efficiently. The newly ignited star enters the main sequence phase of its life, where it will spend the majority of its existence converting hydrogen into helium. The energy produced by fusion counteracts the inward pull of gravity, establishing a delicate equilibrium that allows the star to maintain its structure for billions of years. At this stage, the star's luminosity increases dramatically. The once hidden protostar, obscured by dense layers of gas and dust, now begins to illuminate its surroundings. Powerful stellar winds, driven by radiation pressure and magnetic forces, sweep away the remaining material in the protostellar disk. These winds carve out cavities in the molecular cloud, revealing the young star to the universe for the first time. The ejected material forms glowing nebulae, illuminated by the star's newfound brilliance. Despite its emergence from the cloud, the young star is still far from being fully mature. It continues to accrete material from the remnants of the protostellar disk, adjusting to the demands of sustained fusion. Variations in the rate of mass accumulation can lead to fluctuations in brightness, causing the star to flicker unpredictably. These irregularities provide valuable insights into the early stages of stellar evolution, offering astronomers a glimpse into the chaotic infancy of stars like our own Sun. The transition from protostar to main sequence star is a defining moment in the life of a celestial body. It signifies the culmination of countless gravitational interactions, thermodynamic processes, and nuclear reactions that have unfolded over millions of years. No longer merely a collection of collapsing gas, the young star now stands as a self-sustaining powerhouse, radiating energy across the cosmos. Yet, even as it achieves stability, the star's influence extends beyond its immediate surroundings. The radiation it emits shapes the interstellar medium, ionizing nearby gas and triggering secondary waves of star formation. The birth of one star often sets the stage for the emergence of others, perpetuating the cycle of cosmic creation. With the ignition of fusion, the star enters a new era, one defined by longevity, stability, and the quiet persistence of nuclear reactions. But before it settles into the predictable rhythm of its main sequence lifetime, it must first navigate the complexities of its early youth. The next phase of its evolution will see it refining its structure, shedding excess material, and preparing for the long, luminous existence ahead. The first light a star is born as the final stages of collapse unfold. The young star emerges from its dusty cocoon, casting its first light into the cosmos. The dense envelope of gas and dust that once shrouded it begins to disperse, swept away by powerful stellar winds and intense radiation. These forces carve out vast cavities in the surrounding molecular cloud, revealing the newborn star in all its brilliance. What was once an invisible ember buried deep within the cloud now shines openly, illuminating the remnants of its birthplace. The transformation from a deeply embedded protostar to a fully fledged star is marked by several key events. One of the most striking is the sudden increase in luminosity. As nuclear fusion becomes the dominant energy source, the star's brightness surges, sometimes reaching levels hundreds of times greater than it will maintain in its stable main sequence phase. This burst of energy is accompanied by fierce, stellar wind streams of charged particles accelerated by the star's intense radiation and magnetic fields. These winds slam into the surrounding gas, creating shockwaves that ripple outward like cosmic tsunamis. The impact of these shockwaves sculpts the surrounding nebula, giving rise to intricate structures such as her big horror, objects glowing, knots of gas where the fast-moving jets from the young star collide with interstellar material. The ejection of material from the poles of the young star plays a crucial role in clearing away the last remnants of its natal cloud. These bipolar outflows, launched at tremendous speeds, plow through the surrounding gas, sweeping away excess material and halting further accretion. The process is both violent and elegant, as the newborn star asserts its dominance over its immediate environment. These outflows not only shape the local interstellar medium, but also serve as a mechanism for redistributing heavier elements throughout the galaxy, elements forged in previous generations of stars and now carried outward by the winds of their successors. As the dust clears, the star's true nature begins to reveal itself. Observatories equipped with infrared and optical telescopes capture glimpses of the emerging star, its surface still roiling with turbulence as it adjusts to the demands of sustained fusion. The once hidden protostar, now fully exposed, exhibits characteristics that distinguish it from older, more stable stars. Its atmosphere is highly active, riddled with flares and eruptions as magnetic fields twist and snap under the intense pressures of its youthful dynamo. These flares, sometimes orders of magnitude more powerful than those seen on the modern-day Sun, contribute to the continued clearing of the surrounding nebula, ensuring that the star's light can travel unimpeded across the cosmos. Beneath the surface, the star undergoes a series of internal adjustments. The core, now dominated by hydrogen fusion, establishes a delicate equilibrium between the inward pull of gravity and the outward pressure of nuclear reactions. However, this balance is not yet perfect. The outer layers of the star remain relatively unstable, exhibiting pulsations and oscillations as they settle into their final configuration. These fluctuations cause variations in brightness, making the young star appear to flicker in the night sky. Astronomers study these variations carefully, using them as diagnostic tools to probe the internal structure of newly formed stars and gain insights into the mechanisms that govern their early evolution. The protostellar disk, once a reservoir of raw material feeding the growing star, now begins to thin. Much of its mass has already been incorporated into the star or expelled through outflows, but remnants persist in the form of a circumstellar disk. This disk, though diminished in size and density compared to its earlier stages, still holds the potential for planetary formation. Dust grains embedded within the disk continue to collide and coalesce, laying the foundation for the eventual birth of planets, moons, and asteroids. The fate of these celestial bodies depends on the dynamics of the disk and the gravitational influence of the young star, which will ultimately determine which fragments survive to form stable orbits and which are either consumed or ejected into interstellar space. As the star continues to stabilize, its surface temperature and luminosity begin to settle into predictable patterns. The initial surge of brightness gives way to a more measured output of energy, dictated by the efficiency of nuclear fusion in the core. The star's spectral type, whether it will be a massive, blue-hot O-type star or a smaller, cooler, red dwarf, is determined by its mass, which was largely established during the earliest phases of collapse. Regardless of its ultimate classification, The newborn star now stands at the threshold of a long and stable existence, ready to embark on the main sequence phase of its life. Yet, even as it enters this new era, the star's influence extends far beyond its immediate vicinity. The radiation it emits interacts with the surrounding interstellar medium, ionizing nearby gas and triggering secondary waves of star formation. In this way, the birth of one star often sets the stage for the emergence of others, perpetuating the cycle of cosmic creation. The universe, ever in motion, continues its grand symphony of destruction and rebirth, with each new star contributing its own voice to the celestial chorus. With the last vestiges of its natal cloud dispersed and its luminosity stabilized, the young star now takes its place among the countless others scattered across the Milky Way. It is no longer a mere promise of future brilliance, nor a hidden ember buried in the darkness. It is a shining beacon, a testament to the power of gravity, pressure, and nuclear fire. And though its journey has only just begun, the path ahead is clear. A long, radiant existence, fueled by the fusion of hydrogen in its core, stretching across billions of years, that the stellar family, siblings in the cosmos as the newborn star, begins its independent journey. The story of its origins reveals a deeper truth about the universe. Stars rarely form in isolation. The vast molecular clouds that give birth to stars are rarely solitary nurseries. Instead, they are bustling with activity, birthing clusters of stars that share a common origin, within the remnants of the gas and dust cloud that once cradled the young star. Countless other stellar embryos stir, each following a similar path toward illumination. These sibling stars, born from the same cosmic womb, will shape one another's destinies, influencing their environments and forging connections that span the vastness of space. The formation of multiple stars within a single cloud is a natural consequence of the complex interplay between gravity, turbulence, and magnetic fields. As the cloud collapses, it does not do so uniformly. Instead, small density fluctuations created by the chaotic motions within the cloud give rise to numerous regions where gravity is strong enough to initiate individual collapses. These regions, separated by mere fractions of a light year in the early stages, eventually give rise to distinct stars. Some of these stars form in tight pairs, locked in gravitational embrace, while others emerge as part of vast stellar nurseries, containing hundreds or even thousands of young stars. Binary and multiple star systems are particularly common in the early stages of stellar formation. When two dense cores form close to one another, their mutual gravitational attraction prevents them from drifting apart. Instead, they settle into orbital configurations, circling each other in a delicate cosmic dance. Some binary systems feature stars of nearly equal mass, locked in a balanced orbit, while others consist of a dominant primary star with a smaller companion. In some cases, triple or quadruple systems emerge, where 3 or 4 stars gravitationally bind together, their orbits governed by the intricate laws of celestial mechanics. These multi-star systems are not static. They evolve over time, shaped by the forces of gravity, tidal interactions, and the ejection of surplus members. In the densest regions of stellar nurseries, gravitational encounters between young stars can lead to dramatic consequences. Some stars are flung into interstellar space, becoming rogue wanderers with no home to return to. Others are captured by more massive companions, altering the architecture of existing binary systems. These interactions are especially common in open clusters, where hundreds of young stars are packed closely together, creating a dynamic environment where stellar relationships are constantly shifting. Beyond the immediate neighborhood of the newborn star, entire star-forming regions pulse with activity. These vast nurseries, spanning dozens of light years, are filled with gas, dust, and the telltale signs of ongoing stellar birth. Observations of such regions reveal a breathtaking panorama of young stars at various stages of development. Some are still deeply embedded in their natal clouds, their light barely escaping the dense cocoons of gas and dust. Others have already emerged, illuminating the surrounding nebulae with their brilliant glow. The contrast between these different phases of stellar evolution paints a vivid picture of the continuous cycle of creation unfolding across the galaxy. The influence of these stellar siblings extends beyond their immediate surroundings. As they ignite, their collective radiation begins to ionize the surrounding gas, transforming neutral hydrogen into a luminous plasma. This process, known as photoionization, gives rise to glowing emission nebulae, where ultraviolet light from young stars energizes the interstellar medium. The resulting spectacle, vast clouds of pinkish red gas glowing in the night sky, marks the transition from a dark molecular cloud to an active star-forming region. These nebulae, such as the famous Orion Nebula, serve as cosmic signposts, signaling the locations where new generations of stars are coming to life. But the effects of these young stars go beyond their immediate visual impact. Their powerful stellar winds and radiation exert pressure on the surrounding gas, compressing it into dense shells. These compressed regions can trigger secondary waves of star formation, giving rise to new generations of stars in a cascading effect. This phenomenon, known as triggered star formation, illustrates how the birth of one star can set the stage for the birth of many more. In some cases, the expansion of ionized gas from a massive young star can sweep up surrounding material, forming dense ridges where gravity can once again take hold, initiating new collapses and spawning fresh stellar births. However, not all interactions between stars are constructive. In the crowded environments of stellar nurseries, gravitational interactions can lead to instability. Young stars may pass too close to one another, disrupting planetary disks or even tearing apart nascent planetary systems before they have a chance to fully form. These disruptive encounters highlight the chaotic nature of early stellar life, where the very forces that bring stars into existence also threaten the stability of their surroundings. Despite these challenges, the presence of multiple stars within a single system offers intriguing possibilities for planetary formation. In binary systems, planets can form in two primary configurations, either orbiting one of the stars individually circumstellar, or orbiting both stars together. The latter scenario, famously depicted in science fiction with planets like Tatooine, presents unique challenges, as the gravitational influence of two stars introduces additional complexities to planetary orbits. Nevertheless, observations have confirmed the existence of circumbinary planets, proving that such worlds can indeed exist in the real universe. The legacy of these stellar siblings extends far beyond their early lives. As they age, some stars will evolve into giants, shedding their outer layers and enriching the interstellar medium with heavier elements. Others will end their lives in spectacular supernova explosions, scattering their material across the galaxy and seeding future generations of stars. Even after their individual lifetimes have ended, the bonds between these stars endure, their shared history woven into the fabric of the cosmos. Thus, the birth of a single star is never truly isolated. It is part of a grand cosmic narrative, where entire families of stars emerge from the same primordial cloud, shaping one another's fates and influencing the evolution of galaxies. As we turn our gaze back to the newborn star at the heart of this story, we recognize that it is not alone. It is part of a vast, interconnected web of stellar kinship, each member playing its role in the eternal cycle of cosmic creation. The dance of forces, stability, and equilibrium with the young star, now fully emerged from its natal cloud. The delicate balance between gravitational collapse and nuclear fusion begins to solidify. This equilibrium, maintained by the competing forces of gravity pulling inward and the outward pressure generated by fusion in the core, defines the star's long-term stability. Unlike the tumultuous phases of its formation, where rapid changes dictated its evolution, the star now enters a period of relative calm. Here, in the quiet rhythm of stellar equilibrium, the fundamental forces shaping its existence find harmony. At the heart of this balance lies hydrostatic equilibrium, precise interplay between gravity and internal pressure. Gravity, ever the relentless force, seeks to compress the star further, drawing its outer layers inward toward the dense core. However, the energy released by nuclear fusion generates an opposing force, pushing outward and resisting the inward pull. This outward pressure arises from two primary sources: thermal pressure, generated by the extreme temperatures in the core, and radiation pressure, created by the constant stream of photons produced in fusion reactions. Together, these forces counteract gravity's tendency to collapse the star, ensuring that it maintains a stable size and structure for billions of years. The core of the star, now a furnace of nuclear fusion, sustains this equilibrium through the continuous conversion of hydrogen into helium. In stars like our Sun, this process occurs primarily through the proton-proton chain reaction, where hydrogen nuclei protons collide and fuse to form helium, releasing energy in the form of gamma rays and neutrinos. This energy then travels outward, gradually diffusing through the star's layers until it reaches the surface, where it is emitted as visible light and other electromagnetic radiation. The outward flow of energy not only fuels the star's luminosity, but also contributes to the internal pressure that resists gravitational collapse. While the core remains the engine of fusion, the outer layers of the star play a crucial role in maintaining stability. The radiative zone, located just outside the core, is a dense region where energy moves outward primarily through radiation. Photons produced in the core bounce between tightly packed particles, gradually migrating toward the surface over tens of thousands of years. Beyond the radiative zone lies the convective zone, where heat is transported more efficiently through large-scale movements of plasma. In this region, hot material rises toward the surface, cools, and sinks back down, creating a continuous cycle of convection that helps distribute energy throughout the star. This stratification of energy transport mechanisms is essential for maintaining long-term stability. If energy were to escape too quickly, the star would lose pressure support and begin to contract. Conversely, if energy became trapped and unable to escape, the core would overheat, leading to runaway expansion. The precise arrangement of radiative and convective zones ensures that energy flows outward at just the right rate, preserving the delicate balance between gravitational compression and internal pressure. Magnetic fields also play a subtle but important role in maintaining stellar equilibrium, generated by the motion of charged particles within the star. These fields extend throughout its interior and atmosphere, influencing the behavior of plasma and modulating the flow of energy. In particular, magnetic fields help regulate the transport of angular momentum, preventing excessive rotational speeds that could destabilize the star's structure. Additionally, they contribute to the formation of stellar wind streams of charged particles that escape into space, carrying away excess energy and mass. These winds, while relatively weak compared to the forces at work in the core, provide an additional means of pressure regulation, ensuring that the star does not accumulate excessive material over time. Despite this finely tuned balance, stars are not entirely immune to fluctuations. Small perturbations in the core's fusion rate, variations in the opacity of the outer layers, or shifts in the distribution of mass can temporarily disrupt equilibrium. When such disturbances occur, the star responds through subtle adjustments in its structure. If fusion slows, the core contracts slightly, increasing pressure and temperature until fusion resumes at its original rate. Conversely, if fusion accelerates, the core expands, reducing pressure and cooling until equilibrium is restored. These self-regulating mechanisms ensure that minor disruptions do not spiral into catastrophic imbalances. Over the course of billions of years, the composition of the star's core gradually changes as hydrogen is converted into helium. Eventually, the concentration of hydrogen in the core diminishes, forcing fusion to shift outward into a shell surrounding the core. This transition marks the beginning of the star's later evolutionary stages, where it will expand into a red giant and eventually shed its outer layers. However, for now, the star remains firmly within its main sequence phase, basking in the stability provided by hydrostatic equilibrium. The long-term survival of the star depends on the continued maintenance of this balance. If gravity were to overpower internal pressure, the star would collapse catastrophically, potentially leading to a supernova explosion in more massive stars. Conversely, if internal pressure were to dominate unchecked, the star would expand uncontrollably, losing mass at an unsustainable rate. Fortunately, the fundamental forces governing stellar physics ensure that neither extreme occurs. Instead, the star settles into a state of equilibrium, where the inward pull of gravity and the outward push of fusion energy remain in perfect opposition. This equilibrium not only sustains the star's structure, but also defines its observable properties. The surface temperature, luminosity, and spectral characteristics of a star are all direct consequences of the balance between gravity and internal pressure. More massive stars, with stronger gravitational forces, require higher core temperatures to generate sufficient pressure, resulting in hotter, brighter stars with shorter lifespans. Less massive stars, by contrast, burn their fuel more slowly, maintaining equilibrium for tens of billions of years. Even as the star continues its stable existence, the forces shaping its fate remain in constant motion. The delicate interplay between gravity and fusion will guide its evolution for eons to come, ensuring that it follows the natural progression from main sequence star to red giant and ultimately to its final state as a white dwarf, neutron star, or black hole. But for now, in the quiet stillness of stellar equilibrium, the star shines as a beacon of cosmic harmony, its light a testament to the enduring balance of forces that define its existence. The legacy of light, a star's influence across the galaxy. As the young star settles into its stable existence, its influence extends far beyond its immediate surroundings. No longer merely a product of cosmic forces, it becomes an active participant in the grand cycle of the universe, shaping its environment and contributing to the ongoing evolution of galaxies. From the moment it ignites, the star begins to alter the fabric of space, emitting energy that affects everything in its vicinity, from neighboring stars to the vast interstellar medium that stretches across the Milky Way. One of the most immediate effects of the star's luminosity is its ability to ionize the surrounding gas. As ultraviolet photons stream outward from its surface, they interact with the residual hydrogen and helium in the interstellar medium, stripping electrons from atoms and creating a glowing plasma. This process, known as photoionization, transforms the once neutral gas into a luminous nebula, where charged particles emit characteristic colors based on their composition. These emission nebulae, often appearing in shades of red, green, or blue, depending on filaments involved, serve as markers of recent stellar birth, illuminating the regions where new generations of stars are forming. The expanding sphere of ionized gas, known as an H2 region, grows steadily as the star's radiation continues to penetrate deeper into the surrounding medium. In some cases, this expansion can trigger secondary waves of star formation by compressing nearby gas clouds. As the ionization front advances, it sweeps up interstellar material, forming dense shells of gas and dust that may collapse under their own gravity, giving rise to new stellar nurseries. This phenomenon, called triggered star formation, demonstrates how the birth of one star can set the stage for the emergence of many more, perpetuating the cycle of cosmic creation. Beyond ionization, the star's radiation exerts pressure on the surrounding gas, driving powerful stellar winds that shape the interstellar medium. These winds, composed of high-energy particles accelerated by the star's intense radiation and magnetic fields, push against the ambient gas, carving out vast bubbles of low-density space, known as superbubbles. These structures can span hundreds of light-years, expanding over millions of years as successive generations of stars contribute to their growth. Within these bubbles, the density of gas is significantly reduced, creating regions where future star formation is less likely to occur. However, the edges of these expanding structures often compress surrounding material, forming dense ridges where new stars may take root. In addition to radiation and stellar winds, the star contributes to the enrichment of the interstellar medium through the eventual expulsion of its outer layers. During its later evolutionary stages, particularly as it evolves into a red giant, the star sheds vast quantities of gas through powerful pulsations and stellar winds. This material, enriched with elements forged in the star's corsage, as carbon, nitrogen, and oxygen, spreads throughout the galaxy, providing the raw ingredients for future generations of stars and planetary systems. This process, known as stellar nucleosynthesis, is one of the primary mechanisms by which heavier elements are distributed across the cosmos. The influence of a single star, however, is not limited to its own life cycle. In dense star-forming regions, the combined effects of multiple stars create a dynamic interplay of forces that shape the evolution of entire stellar populations. Massive stars, with their intense radiation and powerful winds, play a particularly significant role in sculpting. Their extreme ultraviolet radiation can strip away the gaseous envelopes of nearby protostars, truncating the formation of planetary systems before they have a chance to fully develop. In some cases, this can lead to the formation of free-floating planets, worlds that were ejected from their nascent systems before they could establish stable orbits. Conversely, the gravitational interactions between stars within a cluster can lead to the ejection of surplus members. In tightly packed environments, where hundreds or thousands of stars are born in close proximity, gravitational encounters between young stars can result in dramatic slingshot effects. Some stars receive enough velocity from these interactions to escape the cluster entirely, becoming rogue stars that drift through the galaxy without a permanent home. Others may be captured by more massive companions, altering the architecture of binary or multiple star systems. These dynamic processes underscore the chaotic nature of early stellar life, where the very forces that bring stars into existence also shape their long-term trajectories on a broader scale. The cumulative effects of stellar evolution drive the overall structure and composition of galaxies. Over billions of years, the continuous cycle of star formation, stellar death, and the dispersal of heavy elements influences the chemical makeup of the interstellar medium. Galaxies rich in old stars tend to have higher concentrations of heavier elements, a result of countless generations of stellar nucleosynthesis. These enriched environments provide the conditions necessary for the formation of rocky planets and complex organic molecules, increasing the likelihood of habitable worlds emerging in certain regions of the galaxy. Furthermore, the explosive deaths of massive stars and supernova events inject vast amounts of energy into the interstellar medium, triggering shock waves that compress gas clouds and initiate new episodes of star formation. These cataclysmic events not only recycle stellar material, but also contribute to the propagation of cosmic rays, high-energy particles, that permeate the galaxy and influence the formation of planetary atmospheres. The remnants of supernova, such as neutron stars and black holes, continue to shape their surroundings long after the explosion itself, exerting gravitational influence on nearby stars and serving as laboratories for studying the most extreme physical conditions in the universe. Even in the absence of supernova, the long-term evolution of stars contributes to the redistribution of matter throughout the cosmos. Loma stars, such as red dwarfs, may live for trillions of years, continuously emitting light and radiation that subtly alters the interstellar environment. Their prolonged existence ensures that their influence persists across vast timescales, shaping the conditions for future generations of stars and planetary systems. Ultimately, the legacy of a single star is not confined to its own lifespan. It extends into the broader cosmic ecosystem, where its radiation, winds, and eventual demise contribute to the ongoing evolution of galaxies, whether through the ionization of gas, the triggering of new star formation, or the enrichment of the interstellar medium with heavy elements. Every star leaves an indelible mark on the universe. As we trace the journey of the newborn star at the heart of this story, we recognize that its influence will echo far beyond its own existence, shaping the cosmos in ways both seen and unseen, echoes of creation. The enduring impact of stellar birth, the birth of a star, is not merely an isolated event. It is a ripple in the vast cosmic ocean, sending waves of influence across time and space. Long after a star has settled into its stable existence, its formation continues to shape the universe in profound ways. The materials it disperses, the light it emits, and the gravitational forces it exerts all contribute to the ever-evolving tapestry of the cosmos. From the smallest planetary systems to the grandest structures of galaxies, the echoes of stellar birth resonate throughout the universe, forging connections between seemingly distant phenomena. One of the most lasting impacts of star formation is the distribution of heavy elements throughout the cosmos. Before the first generation of stars ignited, the universe was composed almost entirely of hydrogen and helium. Remnants of the Big Bang, the heavier elements carbon, oxygen, nitrogen, iron, and more, were forged in the cores of stars through nuclear fusion and later scattered into space through stellar winds and supernova explosions. These elements, collectively referred to as metals in astronomical terms, serve as the building blocks for planets, moons, and even the complex chemistry that leads to life. Without the continuous recycling of stellar material, the universe would remain barren, devoid of the rich diversity of matter that makes planetary systems and biological evolution possible. The enrichment of the interstellar medium with these elements is not a uniform process. Different types of stars contribute varying compositions of material depending on their mass and evolutionary path. Massive stars, which burn through their fuel rapidly, produce and disperse heavier elements like oxygen, neon, and magnesium in their explosive deaths as supernova. Smaller stars, such as red dwarfs, contribute lighter elements over much longer timescales through steady stellar winds. Over billions of years, this continuous infusion of material transforms the composition of galaxies, gradually increasing the metallicity of the interstellar medium. Regions with higher metallicity are more conducive to the formation of terrestrial planets, as the abundance of heavy elements allows for the condensation of rocky material in protoplanetary disks. Beyond elemental enrichment, the formation of stars plays a crucial role in shaping the structure of galaxies. The gravitational influence of newly formed stars, particularly in dense star-forming regions, can alter the distribution of gas and dust, influencing the formation of future generations of stars. In spiral galaxies like the Milky Way, star formation tends to occur in concentrated regions along the spiral arms, where gravitational density waves compress interstellar material, triggering widespread episodes of stellar birth. These waves propagate through the galaxy, orchestrating the rhythmic pattern of star formation that defines the structure of spiral arms. In elliptical galaxies, where star formation has largely ceased, the remnants of ancient stellar nurseries offer a glimpse into the past. The metallicity of stars in these galaxies indicates that they formed rapidly in the early universe, consuming available gas in intense bursts before settling into quiescence. Understanding the differences in star formation rates across galaxy types helps astronomers piece together the evolutionary history of the cosmos, tracing how galaxies have changed over time in response to internal and external forces. Star formation also plays a role in the formation of supermassive black holes, the enigmatic entities that reside at the centers of most galaxies. While the exact relationship between star formation and black hole growth remains an area of active research, evidence suggests that the two processes are intertwined. In the early universe, massive star-forming regions may have contributed to the rapid accumulation of mass in central black holes, either through direct accretion of gas or through the merging of smaller black holes formed from the remnants of massive stars. The feedback mechanisms between black holes and their host galaxies, where energy from accretion disks and relativistic jets influence the surrounding interstellar medium, further complicate the connection between stellar birth and black hole evolution. On a smaller scale, the formation of stars directly influences the development of planetary systems. The presence of a young star dictates the structure and composition of its surrounding protoplanetary disk, determining which materials are available for planet formation. The distribution of gas and dust in these disks is influenced by the star's radiation and magnetic fields, which can either promote or hinder the growth of planetary bodies. In some cases, intense stellar radiation can strip away the gaseous envelopes of forming planets, leaving behind rocky cores that resemble Earth or Mars. In other cases, the presence of a massive star in a binary system can perturb the orbits of planets, leading to chaotic migration patterns or even ejection from the system entirely. The diversity of planetary systems observed in the universe reflects the varied conditions under which stars form. Some systems, like our own solar system, exhibit a stable hierarchy of planets orbiting a single star. Others, such as the TRAPPIST-1 system, host multiple Earth-sized planets around a small, dim red dwarf. Binary and multiple star systems introduce additional complexities, with planets orbiting one or both stars in intricate configurations. These variations highlight the influence of stellar birth conditions on planetary architecture, demonstrating how the initial circumstances of a star's formation can shape the long-term destiny of its planetary companions. Perhaps the most profound implication of stellar birth lies in its connection to the emergence of life. The elements forged in stars' carbon, nitrogen, oxygen, phosphorus, and sulfur are essential for the chemistry of life as we know it. The formation of complex organic molecules, including amino acids and sugars, relies on the availability of these elements in planetary environments. Studies of meteorites and interstellar clouds have revealed the presence of prebiotic compounds, suggesting that the building blocks of life may form naturally in the aftermath of stellar birth. Moreover, the radiation emitted by young stars may play a role in shaping the atmospheres of nascent planets. Ultraviolet light can break down atmospheric gases, leading to the formation of reactive species that drive chemical evolution. On planets with liquid water, these reactions could pave the way for the emergence of self-replicating molecules and, eventually, living organisms. While the precise conditions required for life remain uncertain, the presence of stars and their associated planetary systems provides the necessary framework for its development. The echoes of stellar birth extend beyond the physical realm, influencing the way we perceive the universe and our place within it. Every atom in our bodies, every carbon atom in our DNA, every oxygen atom in our lungs was once forged in the heart of a star. We are, quite literally, made of stardust, connected to the cosmos through the continuous cycle of stellar birth and death. This realization, both humbling and awe-inspiring, underscores the interconnectedness of all things in the universe. As we reflect on the journey of the newborn star at the heart of this story, we recognize that its formation is not an endpoint, but a continuation of an ancient cosmic process. The forces that shaped its birth will continue to shape the universe for eons to come, weaving an intricate web of causality that links the smallest particles to the grandest structures. The birth of a single star is a testament to the enduring power of gravity, the transformative energy of fusion, and the ceaseless cycle of creation that defines the cosmos. A final reflection, the eternal cycle of creation as we reach the conclusion of our journey through the birth of a star. We are reminded that this process is not an isolated event, but a recurring chapter in the endless story of the universe. Stars are born, live, and die, each phase seamlessly flowing into the next, sustaining the cosmic cycle that has persisted for billions of years. The birth of one star sets the stage for the next, as its remnants scatter across the galaxy, seeding the interstellar medium with the raw materials for future generations. This cycle of creation, destruction, and renewal is the heartbeat of the cosmos, a rhythm that has shaped the universe since its earliest moments. Every star that ignites in the vast darkness of space is a link in this eternal chain. The gas and dust that gave rise to the newborn star we have followed were themselves remnants of stars that lived and died long before. The heavy elements that now swirl in its protoplanetary disk, carbon, oxygen, silicon, iron, were forged in the hearts of ancient suns, scattered into the void by supernova and stellar winds. These elements will, in time, form planets, moons, and perhaps even the foundations of life itself. The same atoms that once danced in the core of a dying star now make up the very fabric of existence, binding together in new configurations, continuing the cycle of cosmic evolution. This process is not bound by time in the way we understand it. While human lifespans measure in decades, stars live for millions or even billions of years. Yet, the universe operates on a timescale so vast that even the longest-lived stars are but fleeting sparks in the grand scheme of cosmic history. The birth of a single star is a momentary flicker in an eternal expanse, yet its influence ripples outward, shaping the destiny of galaxies and the formation of new worlds. The energy it radiates, the material it disperses, and the gravitational forces it exerts all contribute to the ever-changing tapestry of the cosmos. Looking outward, we see this cycle repeating endlessly across the heavens. In distant nebulae, clouds of gas and dust collapse under their own gravity, giving birth to new stars that will one day follow the same path. In the remnants of ancient supernova, we find the echoes of past stellar deaths, their material now mingling with the interstellar medium, waiting for the right conditions to ignite once more. Even in the oldest globular clusters, where stars formed shortly after the Big Bang, we witness the lingering traces of this cycle, with generations of stars overlapping in a cosmic family tree that spans the history of the universe. The beauty of this process lies not only in its grandeur, but also in its simplicity. The forces that govern the birth of a star, gravity, pressure, nuclear fusion, are fundamental to the workings of the universe. They are the same forces that shape planets, dictate the orbits of moons, and drive the expansion of galaxies. They are the silent architects of existence, operating tirelessly across the cosmos, ensuring that the cycle of creation continues unabated. Yet, Despite its universality, each star's journey is unique. Some are born in solitude, drifting through the void as lone sentinels. Others emerge in bustling clusters, surrounded by siblings that share their origins. Some burn brightly and briefly, ending their lives in spectacular explosions, while others endure for eons, their slow-burning embers illuminating the darkness for trillions of years. Each variation adds richness to the cosmic narrative, ensuring that no two stars follow the exact same path, yet all contribute to the same great cycle. This cycle extends beyond the stars themselves, the planets that form around them, the atmospheres that develop, the oceans that fill their surfaces, all are products of the same forces that birthed the stars. Life, if it arises, is merely another expression of this ongoing process, a continuation of the cosmic evolution that began with the collapse of a single cloud of gas. In this way, the birth of a star is not just an astronomical event, it is the beginning of a story that may one day include civilizations, cultures, and beings capable of looking up at the night sky and contemplating their place in the universe. As we stand on the precipice of understanding, we realize that we are not separate from this cycle. We are a part of it. The atoms in our bodies, the air we breathe, the ground beneath our feet, all are the remnants of stars that lived and died long before us. We are stardust given form, consciousness arising from the ashes of ancient suns. Our existence is a testament to the resilience and creativity of the universe, a reminder that even in the vast, indifferent void, meaning can emerge from the interplay of forces that govern existence. And so, as we conclude this exploration of stellar birth, we do not say goodbye to the star at the heart of our story. Instead, we recognize that its journey is far from over. It will continue to shine for millions or even billions of years. Its light traveling across the cosmos, touching distant worlds, perhaps even illuminating the eyes of future observers who will one day look up and wonder at the mysteries of the universe. Its influence will extend beyond its own lifespan, shaping the interstellar medium, seeding new generations of stars, and contributing to the ever-unfolding story of creation. The birth of a star is not an endpoint, but a beginning, a spark in the infinite dark, a beacon of possibility, a reminder that the universe is alive with motion, transformation, and wonder. And as we drift gently into the quiet vastness of space, we carry with us the knowledge that we are part of something far greater than ourselves, forever connected to the stars that came before us and the ones yet to be born.